working. Thank you. So before we start with a new topic today, that's going to be on work and energy, I would want to wrap up that problem that we were talking about. So did we get a chance to think about that tube problem with non-inertial frames? So I asked you a question. If in that rotating tube, you were sitting at a distance from the plug's moving with r dot, that is controlled by the spool, versus if you are moving, if you are sitting on the plug, will you see the motion of the plug differently in the two cases? So in one case, I am sitting halfway through the tube and seeing the plug. I am rotating in the tube, and the other case I am sitting on the plug. The question to answer here is the acceleration of the person on the halfway mark and the acceleration of the person sitting on the plug, are they the same? They are not the same, right? So if they are not the same, then they will not see the acceleration of the plug as the same. Relative accelerations. So it's always recommended that you solve the problem. The stuff will work fine if you work in any frame. They are both non-inertial frames, so you can choose any frame you want in case you really are adamant about using a non-inertial frame. But in case you want to use a non-inertial frame, sit on the object. That is always mathematically convenient. In case we sit on the object, then we see the object's acceleration as 0 in our frame, right? So now to be able to apply Newton's law, Newton's second law, we will have to add our true force or true forces with a fictitious force, and that will be equal to mass times acceleration, and this acceleration is measured from the non-inertial frame. So we use subscripts where we said subscript means where it is measured from, and this is 0 because the acceleration of the object from our non-inertial frame is 0 because we are sitting on the object. Of course, in that case we will see the object stationary because we are both having the same acceleration. Okay. Relative acceleration in that case becomes 0. So if I look at the two forces, so one is tension, that's one of the true forces we had, and the other true force we had for case A was an F theta that was actually coming from normal. So these were the two true forces. Now we have to make sure the true forces become 0. So, we have to add a fictitious force so that the apparent force now 0. So we have to add, let's use red color for this, a force opposite to tension, right? And what is the radial acceleration? R double dot minus R theta dot squared. Now AR is 0 because we know the force in radial direction net is 0. So that means R double dot becomes R theta dot squared. In this case, we need R theta dot squared acting outwards to balance this tension. Is that clear? Yeah. Oh, I'm sorry. No, wait. Sorry for that. I was again thinking in inertial frames. Yeah, in non-inertial frame, the apparent force is 0. So excuse me for that. So F true is equal to negative F fictitious. So we showed that the tension in the earlier case was equal to the centripetal force. So opposite to the centripetal force is what we need. So what we need is exactly equal to m times r theta dot square that's acting outwards. And this is what we call the centrifugal force. Is that clear? So this is F fictitious, the radial coordinate. And remember, this was equal to m times negative of the frames, non-natural frames reference. So this is me sitting on the object, my acceleration with a negative sign. So my acceleration, in this case, this is me. So my acceleration is r double dot is 0 because I'm sitting on the object. So r dot was constant. So it's simply centrifugal. But there is one more component. Centrifugal is something we already have known. The other one, my a theta is also there, right? That is 2 times r dot theta dot. Now this may seem trivial because we are sitting on the object, so we are solving the same problem. All right? That things can get complicated if you are sitting somewhere else and you are moving with a different acceleration. And we will do that later when we talk about rigid bodies. But for now I am just giving you a feel because many people were reading about Coriolis forces. So a theta for me as the person sitting on the object is there. So that's the non-inertial frames a theta. So when we apply the centrifugal force, then that is when we apply when we want to find the fictitious force in the theta direction, that is simply mass times negative of the frame's reference. So the frame has an acceleration of 2r dot theta dot, so it becomes opposite. So it simply becomes opposite to the normal reaction. And this is what we call the Coriolis force. So these are fictitious forces that one has to add so that you can still apply Newton's second law, and we saw that this Coriolis force was simply equal to whatever the normal reaction was in the opposite direction, which is 2 times r dot theta dot, but in this case opposite. And this force is perpendicular to theta dot. If you were to think of theta dot as a vector, again we are not doing that right now, but we will do it later. So theta dot is the rotation. So if you see from the top, the rotations in this free body diagram is happening in a plane of the sheet. So my direction is normally outwards for the rotation, for the angular velocity vector, and my r dot is radially outwards. So we see that this Coriolis force is always perpendicular to both theta dot vector and r dot vector. R dot is from left to right here, and theta dot is outside the plane of the paper. So this is mutually perpendicular to both, that is F Coriolis. The sign, of course, we'll worry about later when we actually give you the vector expression for that. So that is all we want to discuss about this fictitious force called Coriolis force. So please do not confuse with the fact that Coriolis acceleration is fictitious. It is simply an acceleration, nothing else. And that is 2 times r dot theta dot in the theta direction. Is that clear? So try to work in the inertial frames and your life will be much more comfortable. So this is all to satisfy those who was trying to understand what Coriolis force means. We will not take up this problem any further in the next few lectures. Now a question for you. In this case, we had 2 fictitious forces, what if we also have a non-zero theta double dot? It's an angular acceleration. You can have that, completely allowed. Till now we were taking theta dot equal to omega equal to constant, but it may not be necessary. So let's say theta double dot was non-zero. Will you have another fictitious force in this problem where you already have two fictitious forces? Think about it. For those sitting at the very back, can you read what I'm writing? You can read that, what's on the board? Okay. Now we'll do a quick recap of work and energy, and then hopefully we'll be able to solve some problems. Now this is another approach. Whenever a problem does not work out or is getting too complicated with F equals ma, we were applying the work energy approach. That is what we were doing. So what we do in this approach, let's say we are dealing with a linear one-dimensional motion. So in that case, kinetic energy for an object, single particle moving in a straight line is half mv square. You differentiate that with respect to time. Everything happening in a straight line. So this is called the work energy theorem. Okay. But now that's not the best way to represent this theorem or to reach this theorem, but this is one of the ways we were able to reach this. So we start with kinetic energy being half mv square for a given particle. We differentiate that with respect to time, and then I find what basically I am getting rid of time here. So we get rid of time. So we have a small change in kinetic energy is equal to f times dx. And then we integrate that over the complete motion from x1 to x2. Let's say the particles going from x1 to x2. So what we get is the change in kinetic energy is equal to the work done by the force F on the particle. Right? And F is the only force acting. So that's the only force resulting in the change of kinetic energy. That's one dimension. Now in 2D or 3D, we can approach, we can reach the same result in the vector form, and we'll do it more systematically. So we'll start with Newton's second law. So the net force acting on a particle is m times its acceleration. Now we take a dot with dr on both sides. So dr vector is displacement vector. Dr can be written as v times dt. Now if we take v dot v and differentiate that with respect to well, simply take the change in v dot v. So what we get is twice of this quantity. So I can divide this by 2. So this allows me to do this. And v dot v is simply the square of this magnitude of v. So now we can integrate both sides. And we'll integrate from a to b. So we are moving in a plane or in a three-dimensional space from point A to point B along a certain path, and this we will say that the velocity magnitude at point A was v subscript A and velocity magnitude at B was v subscript B. That's the work energy theorem in general 2D or 3D motion. So we can write this as this integral that we have here is a line integral. So this is along, well, we call it a line integral, but it's along a curve. So if you look at, let's say, the path from A to B was something like this, and what we are doing is we are doing f dot dr. So dr, again exaggerating things, let's say this is my dr. I find the force at point A and take a dot with this vector dr. So let's say force was like this, and then find f dot dr, the scalar f dot dr, and then add the next part of the motion. So next displacement is like this, and let's say the force now is acting like this. Of course, I mean there won't be a sudden change because we are talking about continuous change, but I'm just trying to show you that as we move from A to B, the vectors f and dr will change. Dr will change according to your path, and f will change according to however it is defined. It depends on your force field. So f dot dr is what has to be added, the contribution of this. So the small work done in each step has to be added to find the total work done. Okay. So this f dot dr integrated over A to B is a line integral. We will do more practice on this line integral. Have you done line integral? I think you are doing a course in electrodynamics, right? No, you are doing. Who is doing this course? Third year. Oh, okay. Then do we understand what gradient, divergence? Can I get a raise of hands who have never studied about this gradient operator? Divergence, curl, all these words are new to you? Okay, that's fine. So we will talk about that. Well, you understand the idea of line integral? Okay, so we are moving on a line. Now if I change my line, I can go from A to B along a different path as well. So if I go along a different path, let's say the gray one, I could have a different value of the line integral, right? Because my force would be different there. dr is different. So we could have a different value of this integral. So line integral has to be calculated along a path. So you have to define what path you are moving on. We'll come back to this later because this is a bit confusing. If we already know the path, we already know how the motion is happening, then why are we doing all this? Force is given. The problem in mechanics is you give me a force, I'll find the motion. Motion is acceleration, velocity, position. But if I already know how the particle is going, then do we really need to use this? We'll come to this. This is useful. You have used it in the past, we'll still use it. So there are certain situations where this approach is useful. Let me ask you a question, a more philosophical question here. Why would we use the work energy theorem as opposed to Newton's second law? Because this is just obtained from Newton's second law. I started with F equals ma and got the work energy theorem. That is, the change in kinetic energy is equal to the, well, we haven't been writing this, so this is the work done by the force F on the particle. So whatever work the force does, that results in an increase or decrease in the kinetic energy. There is no work done, the kinetic energy will not change. The more philosophical question is, why work energy theorem? Anybody wants to hazard a guess? Okay. But here you agree with the fact, so the answer is it follows law of conservation of energy, the mechanical energy. And that is right, but the thing is that it is coming from F equals ma. So we are deriving something from F equals ma, then why not use F equal to ma? We know the force, we can find the acceleration, and we can integrate that to find the velocity and position. Force is given. Okay. Force is given, that is I am telling you, in both cases. You cannot apply the work energy theorem without knowing the force. You have to find the work done. Raise your hands, please. Conservative forces, okay, we'll come to that, yes. We are getting there. Time, yes, that's a very good point. What if force is given as a function of position? Force can be changing, right? Force can be changing with time or position. So if force is given as a function of time, you will use F equals ma. Because F equals ma, acceleration is second derivative of position with respect to time, or first derivative of velocity with respect to time. But if force is given as a function of position for some situation, we call it a force field. If you have a force field given to you, then it becomes force vector as a function of x y and z, or we can say simply as a function of r equal to m times d r. So you have r as a variable, r is changing, t is also changing. So this equation becomes complicated. But if you look at the work done here, we got rid of time. All we have is f as a function of r dotted with a dr. Life looks very comfortable here. So that's one situation. Yes. Rid of time. What's the another one? Radius of force was constant. Then this complication is gone. Let's say I want to find velocity. That happens. I want to find the velocity of a particle as it goes from point A to point B. How is that changing? What is the velocity at point B? That is what you have to find. That's what is given in the problem. How will you solve that in Newton's second law approach? You know force, you'll find acceleration, all the components of acceleration, then you'll integrate that to find the velocity. That integral could be complicated. Is that integral even appearing here? You straight away get the velocity because you integrate f dot dr, and that's change in kinetic energy. So if you want to find velocity, if your aim is to find velocity starting with force, then an intermediate acceleration is needed in the Newton's second law, but you can straight away reach this in work energy theorem. We have to keep these things in mind when deciding which approach to use, because now we will not have representative problems. Oh, this kind of a problem I have to use work energy approach. That was old times. Now we have to think more structured, in a more structured sense. Is that clear? Right, so moving on. So this dW, that's the small amount of work done in a small step, is f dot dr, and f dot dr, f has two components here. One is along displacement, if you think of the nt coordinates. One is a tangential component, and one is a normal component. And the displacement, of course, is ft is defined in the direction of velocity or displacement. The Fn does not do any work. It is only Ft that does work. If you had a problem where you only had a normal force, then you will not have any work done. That will not result in any change of kinetic energy. Okay? So we understand if you take a string and rotate it, then the tension that we have here is simply acting normal to the direction of velocity. So there is no work done by that. And that is the reason you do not see any change in the magnitude of velocity. There are forces that simply rotate the velocity vector, and these forces have no contribution towards increasing the velocity. If you have any component of a force or acceleration in a direction which has any component along tangent or tangent, in that case you will have work done. So that is another way to think. If you're dealing with forces, many forces, and most of them are simply changing the direction of velocity or are perpendicular to velocity, then you don't need to worry about that. But if you're using a Newton's second law approach, you have to worry about that, right? But here, you only talk about the active forces. So rather than drawing a free body diagram, we draw an active free body diagram, where we only show forces which are doing work. That makes life one step easier. But it depends on the problem, of course. But these are potential things we have to keep in mind when deciding what approach to use. The Fn is called a reactive force, just a term, and Ft here is called an active force, component of force. So F by itself is an active force because it has a component along tangent, but Ft is called an active force component and Fn is called a reactive force component. Then this concept of power. I have a powerful motorbike. What does that mean? Does it mean it can do a lot of work? It can transfer a lot of energy? The power means it can transfer a lot of energy in a unit time. Of course, you take an old motorbike and the engine can give you millions of horsepower over a long time. But what matters is how quickly can you do work? And engineering wise, I mean, thermodynamically you always worry about work. But that is not much of a use in the sense that how long do you want that work in? You want the energy quickly. You want a big motor. You want a big air conditioner because you want to do a lot of work in a very small amount of time. Okay, so power is dW by dt, so that becomes F dot V. So P is typically used as a measure of the capacity of a machine. Okay, yeah, starting the motion is a bit complicated because in the beginning the velocity is 0, right? So imagine, I mean, you take a string. First, what you do is you give it a velocity, the stone the velocity, and as soon as you give it a velocity, then you provide tension, you hold the string tight. Okay, you take it on a plane, flick this stone, and then you have to give it a velocity. We solve these kind of problems in the next approach, that's called the impulse momentum approach. Typically there are three ways to attack problems. One is the force approach, F equals ma. The other is the work energy approach, and the third one is impulse momentum. So impulse is where the forces act for a very short time. So you have to give the stone a speed to start with, and then you get a steady situation. You can do a lot of things, but the point is, what are you asking? Okay? So if you want to understand the motion, yes, to change motion you have to do something, you apply some force. Now, what are the types of forces we work with? We can have a constant force. An example would be mg. mg is constant for a given mass. We don't go too far away from the surface of Earth. So what is the work done in this situation? So let's say that we are working in a two-dimensional system where gravity is acting in the minus y direction. Now dr is a displacement. So dr has components along x and y. So dx along I hat and dy along j hat. We do a dot product. Let's say y goes from 0 to h in this case. So this becomes minus mgh. This is something interesting we see here. It only depends on y. Right? It only depends on y. It only depends on the change in y. I could have taken any path. So when I integrate over a certain path, what I am saying is that there is a constraint. If you give me a certain change in y, then the certain change in x is dependent on that. That's what a path means. If it was a completely independent, a completely arbitrary motion, then dx and dy will have no relation. But if you move in a path, then your dy and dx will be related. Okay. But it is not dependent on path at all. It only depends on ya and yb. So this kind of a force is called a conservative force, where the work done by the force does not depend on the path. And this is where we don't need to know the path. In the beginning I told you, what is the point of using this approach if you have to integrate the force over a certain path? You will be expected to know the path. But no, you are not expected to know the path in this approach if you are dealing with a conservative force. The second kind we deal with is spring forces, or spring force. That depends, so the force depends on the deformation in the spring. So if you extend a spring, the spring wants to come back. If you compress a spring, the spring wants to go back to its mean position. So deformation from the mean position. If I take a mass connected to a spring, and I am moving the mass from left to right, the mass is moving from left to right, from x equal to x1 to x equal to x2. Now the spring will apply a force to the left. In this case, when we are extending the spring, in this case we see an f and dr in opposite. Dr is simply has a dx I hat. F has a minus kx times I hat, that's my f, and dr of course is general displacement. So we see that this becomes minus kx integrated from x1 to x2. Again we see that there is no dependence on the path, right? It only depends on x1 and x2. How it went from there from x1 to x2, we don't care. Doesn't matter. So again, we have a conservative force. I may give you a new kind of force to work with in a problem. You have to figure out whether it's conservative or not. Only then you can apply the idea of potential energy. That's what we'll talk about now. Well, the third kind is your F is perpendicular to velocity, but that doesn't do any work, so we'll not talk about those forces. Now some questions to reinforce our understanding. You have to tell me whether the work is positive or negative. So there's a mass that moves up against gravity. Is the work done by the force of gravity on a mass moving up positive or negative? Because direction of force and direction of displacement, they are opposite. What about a spring that is stretching and applying a force on the mass? So what's the work done by the spring force that is stretching on a mass? Negative? What about a spring that is compressing? How can a spring stretching also be negative and compressing also be negative? In both cases, the direction of force on the mass is opposite to the movement. If you compress, if you are moving a mass while compressing a spring, what happens is displacement and force on the mass are opposite. What about a spring that is initially stretched and now moving towards its mean position? And that is positive. And the same holds for compression as well. So we have to be careful. We sometimes make a mistake saying that it's compressing as opposed to stretching, so the sign changes. That is not the case. Well, good. Now let's say we have a system of two particles. Let's say there are two charges, and this is particle A and particle B. The particle A is being attracted towards B with a force FAB, and B is again attracted towards A with a force BA. And we know how FAB and FBA are related. Okay? Newton's third law. The work done on A by this force is, so A goes from A1 to A2 under the action of force AB, and displacement is dx. Similarly, the work done on B by the force FBA is this. And from the work energy theorem applied to each and every particle separately, I can write this as that's a change in the kinetic energy of particle A. And this is for particle B. I can add these. On the right hand side, what we have is the kinetic energy at position 2. Well, we shouldn't say position 2 because the position 2 can be different for the both particles. Let's say kinetic energy final of the system minus kinetic energy initial. The system is two particles. So the final kinetic energy of the two particles minus the initial kinetic energy of the two particles. And that is the work done, total work done on A and B. Now these, when you have a system of two particles and the particles are applying equal and opposite force on each other, these forces are called internal forces. Right? So for a system, internal forces are internal, they are applied by the particles between each other. Now the tendency we have is internal forces get cancelled, they are equal and opposite. So should the work done because of internal forces also get cancelled? No, because in this case we see that the particles particle A moves to the right under action of force that is acting on the right. So the work done is positive. It's a scalar quantity, it's a positive value. The work done on B is also positive, moving to the left under a force that is acting on the left. So when you apply the work energy theorem, we have to say that the net work due to internal and external forces acting on a system is equal to its change in kinetic energy. Remember, if you are dealing with a system, you have to also consider the internal forces, if of course they are doing work, and in this case they are doing work. Don't just neglect them. So now we are coming towards defining a potential energy. By the way, we talked about conservative forces. So conservative forces are forces where the work done is only dependent on the initial and final position by a given force. That force is called conservative force. Can you give me an example of a non-conservative force? Friction. Is that friction path dependent? You take a longer path, potentially you'll end up having more work done by friction. Okay? So friction is a non-conservative force. Good. So let's now define potential energy. So we are dealing with a system with internal forces, and these internal forces are conservative. So we have a system with conservative internal forces. So we define the change in potential energy as the negative of the work done as you go from initial to the final position. And the hint was that the work done was dependent on initial and final position only. As we saw in a spring, half kx 1 square and half kx 2 square. So this was the hint for us that we can define a quantity associated with that position. It's only that quantity that changes. The other hint is, the other idea is, why is it called a potential energy? It has a potential. If you take a spring and stretch it, it has a potential to come back. That potential is why we call it a potential energy. So now we apply the work energy theorem. So this work energy theorem is being applied to this system where only conservative internal forces are acting. There is no external force acting. The only forces are internal forces which are conservative. So we just saw that work done can be written as minus of uf minus ui that tells us for this system we have the sum of kinetic and potential energies initially is equal to sum of kinetic and potential energies finally. So we call this sum of kinetic and potential energy as the total mechanical energy, in this case as capital E, and this is called the conservation of mechanical energy. Now remember, there was no external force acting on the system. It is only acting under internal forces. If I allow an external force to act, then will this be valid? No, I mean if you have a work that is done from an external force, that could increase the energy of the system overall. So this will only be valid when there is no external force. What if my internal force here was non-conservative? Could I apply this? Let's say two blocks were sliding over each other. The force of friction is internal. They are equal and opposite the way blocks apply, but the system will lose energy. So I cannot say that initial energy is equal to the final energy. You can apply this when no external force is acting, or the work done by external force is 0, and the internal forces are all conservative in nature. We have learned all this. Okay, I am just recalling this because I don't want you to be confused with the basic ideas and not being able to understand the problems. So I cannot apply this if we have a non-conservative internal force. Can I apply the work energy theorem in general if my internal force is non-conservative? Can I apply the work energy theorem in general if I have non-conservative internal forces acting? I can. The work energy theorem still can be applied. So don't be worried that no, the internal force is non-conservative, so I cannot use the approach of work energy. You can. It's only that you cannot use the energy. If you think about it, I mean, this doesn't make sense for non-conservative forces because energy is getting lost. Right. One last question and then we'll close. Now, with the existence of a potential energy function, I have two approaches now to deal with a problem that has a conservative force. So one is I can simply find the work done and apply the work energy theorem. I don't even have to think whether the force is conservative or not. I find the work done and equate it to half mv2 square minus half mv square, v1 square. The other way is I deal with the potential energy. Now the question is, why do we prefer to use potential energy rather than integrating over the whole path? Exactly. F and R relation might be very complicated. You take a spring and you have a spring that is acting at an angle and the object is moving in a curve. So think about this problem where you have a channel, the object is moving in this channel from A to B, and there is a spring that is acting like this, and the spring can rotate about this point. Try to solve the problem with finding the work done. It gets very complicated. You don't need that because what matters is the spring. If you take the spring and the mass as one system, you can easily find the energy, initial spring energy and the final spring energy, right? So if you have a conservative force, go for potential energy approach rather than finding the work done over a path, because the relationship between force and displacement in that path could be quite complicated. You don't have to worry about the path at all anymore because it's a conservative force. Right, so we'll stop here. and from next time I'll be able to talk about work and energy in a more advanced sense by solving problems. Next session is a tutorial. I'm sorry I did not upload the tutorial sheet. I will do that as soon as possible. So we'll have a tutorial on Wednesday. Thank you.